Hey, good afternoon, everyone, and welcome to Leveraging Classical Infrastructure in Quantum-Enabled Environments, offered in partnership with Dell Technologies. This session is the first of three that we are hosting together with Dell. My name is Rachel. I'm a part of UBC ARC team supporting research engagement and training. We're really glad you could join us today as part of the 2026 ARC Summer School. Just a quick note that the session is being recorded and will be uploaded to our YouTube channel. The link to the video will be shared with you after. Just a few quick housekeeping notes before we get started. Please use the Q&A or the chat feature if you have any questions throughout the session. You're also welcome to submit questions anonymously if you prefer. A quick reminder that to comply with UBC's privacy guidelines, external AI transcription or recording tools are not permitted during the session. We appreciate your help with that. Before we begin, I'd like to acknowledge that UBC's Vancouver campus is located on the traditional, ancestral, and unceded territory of the Musqueam people, and the UBC Okanagan is situated on the lands of the Okanagan Nation. We're grateful to learn, live, and work on these lands. I'm now pleased to introduce today's presenter. Burns Healy is the Quantum Infrastructure Lead at Dell Technologies. He holds a PhD in mathematics and specializes in quantum hardware and algorithms, as well as how to effectively leverage modern classical server and high-performance computing infrastructure alongside emerging technologies. During his time at Dell, Burns has applied over 65 patents. More recently, has been working with Dell supply chain to explore how modern heterogeneous computing workflows can improve outcomes for complex optimization problems. We also have Lori from Dell who will be supporting the session today. And with that, I'll pass it over to Burns. Over to you.
Thank you so much. I appreciate the introduction. Thank you to everybody for being here. And I will share my screen in a second. But before I do that, let me just encourage that I would love to hear questions. Anything pops into your mind, drop it in the chat. I really want this to be conversation back and forth. And really my goal here is to help y'all learn what you want to learn. So if there's something you want to dive deeper in or something I said that you want more clarity on, please just feel free to drop it in and we'll chat about it. So that being said, I do have a deck that I'll be working from, but like I said, we can kind of go back and forth and drill down on whatever makes the most sense. So I'm going to try doing the presentation in Teams. My understanding with this is that you also have the ability to go back and forth on slides if I do this properly instead of a normal screen share. So if that's not the case, I apologize, but I think that should be how it works.
We can do that, yes.
They can. Oh, great. Fantastic. Awesome. So real quick, I just want to flag here that I work in Dell's research office, and a little bit about what that means is that we focus on emerging technologies. So quantum computing is one of those. Until recently, AI agents was emerging. Now I would say it's emerged. But advanced security, immersive enterprise, these are sort of the topics that we look at. And so just a good maybe an advertisement for this kind of position if you're still doing your studies is that I find working in a research office within a larger company to be kind of the best of both worlds between the agile nature of a startup but with the stability of a large company is something I've really enjoyed. So consider that. But we're not here today to talk about jobs. We're here to talk about quantum. And specifically, we're here to talk about quantum in classical infrastructure in quantum environments. So what does that mean? So right now I'm talking about you have a quantum device. I'm going to avoid using the word quantum computer. The reason I want to avoid that word is because a quantum computer sort of has this implication that it is a standalone device. It has a quantum monitor and a quantum keyboard and a quantum hard drive, and a quantum memory, and it has none of those things, right? It's not a quantum computer, it's a quantum processor is the way I promote thinking about it. So the term QPU is one that I prefer, quantum processing unit. That's how I'm going to refer to quantum devices going forwards. Is there a future in which there's something called quantum memory? Yes, we can talk about that later. But for now, I want you to think of, whenever I say quantum device, quantum accelerator, I want you to think of something like a GPU. Okay, it's going to be a specialized device that is good at certain tasks and not good at other tasks, and we'll get into exactly what that means as we go forwards. So quantum doesn't live in a vacuum because if I just hurled a graphics processing unit, into a data center, nothing would happen, right? It needs to be on a board. It needs to be connected to other resources. It needs to be in a server. It needs to be provided power. And the same thing is true of quantum compute. Okay, quantum compute itself doesn't live in a vacuum, and it can only do workloads that have been kind of pre-processed for it. So if I am trying to program for a quantum device, I need to think in quantum algorithms, write something called a quantum circuit, and that quantum circuit needs to be interpreted. Okay, and so when I program for a quantum device, I can do that from my laptop or from an HPC environment from anywhere, but I'm working in a digital world, right? I'm working in zeros and ones. And if I was just restricting myself to zeros and ones, then there would be no quantum advantage. Quantum computing works on the principle that I have various advantages like quantum entanglement, quantum superposition. Okay, superposition being the idea that a individual unit of computation, which is called a qubit, can be in a superposition of 0 and 1 at the same time. And for the purposes of this hour and a half, I won't go into the underlying physics of that. That's its own separate rabbit hole. So for now, we'll just kind of assume that exists, and it does, and that we can manipulate it. But the idea then is that when I have now a single qubit, there's infinitely many states it can hold. It can be 0, it can be 1, it can be 1/10 0 and 9/10 1, it can be 1/10 1 and 9/10 0, and everywhere in between. In practice, we're limited a little bit by precision. I can't get arbitrarily precise because I'm still using physical means of manipulating this fundamental unit of computation. But in practice, it means that the world of possible states of any given data structure that I'm manipulating is exponentially increased. So in essence, then what we're doing is we need to take our digital instructions, turn them into some level of quantum instruction, and then get the results out. Okay. And so what that means is that I've got steps I have to do before going into a quantum processor to prepare it into, quantum ready state. I'm getting out quantum output, and that needs to be reinterpreted back in the context of my original problem. And even while the quantum processing is going, there are various roles for the classical infrastructure to play to support a QPU. So at all stages while a quantum workload is being executed, classical gear, and when I say classical, I just mean non-quantum CPU, GPU, servers, those sort of objects, those are in full force being used to provide value and to actually enable the quantum processor. So what does a workload look like when we're talking about a quantum job or even a hybrid job? A hybrid will just mean a workflow that has some quantum components and some non-quantum components. Then that's going to be a little something like this. Again, we're starting, let's see if I've got a laser pointer. I do, right? When I do that, can y'all see it? And I'm just going to
Yes, we
also
can
see
see
if
it.
you're perfect. Thank you. So you're starting at a server, you're starting on a Dell laptop somewhere, you're starting from an HPC environment, what have you. And so if you're coding for a quantum algorithm, you're likely still using something like a VS code, right? You're going to be using these familiar tools, and you're writing some kind of binary that eventually gets fed into the quantum accelerator, writ broadly. So what does that look like? So I have digital set of instructions, and I send those into the quantum accelerator. So the quantum accelerator itself is a stack, and I'll just preview. We'll talk about the hardware for it on the next slide, but first I want to start with just the top level workflow. The quantum accelerator is a stack, and that actually starts on another server whose sole job is dedicated to being the host for that device. So again, the QPU doesn't have memory, it doesn't have storage, right? It doesn't have these other things. It relies on classical hardware for those. So this real-time host, as we're calling it right here, is providing those resources to the QPU. The QPU isn't attached like a PCIe device, unfortunately, into the server, but you can almost think of it that way. You can abstract it away as being the separate compute resource available to this real-time host server. Okay, but again, like I said, this real-time host server is still speaking digital instructions. It's still in zeros and ones. And I said that the power of quantum computing lies in that superposition idea. There's more to it, but you can boil it down to the idea of there being way more instructions and way more states available to the QPU than we have on CPU or GPU. So if I'm restricting myself to purely digital 0 or 1 instructions, I can't harness that advantage. I can't execute quantum enabled workflows if I'm restricting myself to not, and, or, XOR, etc., which is what this server is going to speak. So that means I have to move into the world of analog signals. So that's exactly what this quantum controller box is going to do. It's going to take my quantum circuit, my quantum algorithm that I've developed, where it says at this point, apply this analog instruction to that qubit, and at that point, entangle these two qubits so they're statistically dependent on each other, and such down the line, right? I write this high-level program that's going to get compiled. So this quantum controller is going to compile that into a series of analog impulses. Now, what this looks like depends on the QPU. Okay, so some QPUs are superconducting, some are trapped ion, some are neutral atom. These are all like way different ways of doing quantum computing. I usually say that this is a VHS Betamax thing, and then I realized that reference was getting a little dated, so I updated it to saying it's kind of like a Blu-ray DVD thing, and then I realized that reference was getting a little dated, and then for a while it just like felt awful. But suffice to say, there's competing ways to implement this technology. There are a number of different architectures that can implement the same idea of a qubit, of entangling two qubits, of applying these quantum gates to them, of doing quantum computation on them, et cetera, et cetera. So this quantum controller is going to take our digital abstract idea of a quantum workload, a quantum algorithm, and it's going to turn it into specific analog instructions that will go to the QPU, and it will control this qubit at this time, this qubit at this time. And when I say time, I really mean to emphasize that because we're talking about nanosecond level precision here. So this quantum controller, you should think of as a very big DAC, which is digital analog signal converter, with very precise timing requirements. So it's going to send these often radio frequency level instructions down to the qubits. In here, the magic will happen. I won't, again, get into exactly how that magic happens because it depends so widely on how it's being done for that particular environment. But suffice to say, it does some physical manifestation of the instructions you've written in your quantum algorithm. And then you get results back out through the controller. This is often a pulse processor. And then that will convert back from analog into digital, give you your answers, and then you'll end up back in the world of HPC. So that's high-level workflow. If you want to look at it from a hardware perspective, this is a fairly decent representation of what this is. So we've started up here, quantum hybrid workload. What is this picture representing? So one of the major applications of quantum computing that we're expecting to see provide some kind of advantage over classical approaches is molecular modeling, molecular simulation. Okay, so if you think about applications of material science, you think about biology and chemistry, you think about drug discovery and pharmaceutical companies. Really what they need to do to be able to be successful in those areas is to understand how molecules or even atoms will interact at this kind of quantum level, right? If I'm talking about bringing two compounds into contact with each other, knowing what's going to happen in, say, a chemical reaction, really can't be figured out easily by HPC. And the reason is because they have quantum effects. Quantum effects are very small, so on a day-to-day level, we don't care about them. We can ignore them. That's where Newtonian physics comes from. But in that microscopic, like that atomic level state, those quantum effects are big enough that they have to be considered, because if you don't consider them, your answer will be wrong. It will just be far enough from reality that it's not useful. So you have to model quantum behavior for those problems. And that's just something that's extremely difficult for classical computers because, like I said, there's all of these degrees of freedom. There's all of these different parameters that need to be accounted for. So why are we expecting QPUs to be any better? It's because they're naturally already speaking that language, right? If I need to think about the entanglement between two compounds as I bring them close to each other, that entanglement is very concisely expressed by my qubits, by my QPU. So I would say it's a tangent. It's not a tangent. That's an important point here, but that's kind of a long story as to why this picture on the screen looks like that. So I have this. Molecular simulation problem that I want to send to the QPU. Now, of course, that's part of a larger workflow, a larger pipeline that might be doing several classical things, and then it wants to estimate the ground state energy of this compound, and then needs to go on and do other classical things. So you're not going to see quantum accelerators in isolation. You will almost always see them connected to some data center or some advanced HPC environment over here. And the reason for that is simple. It's because you want to assign the things that are good for quantum devices to do to the quantum device, but anything that's not useful to do on a quantum device, you want to use HPC for that because HPC is cheaper, right? We have a lot of HPC. We have very few quantum devices that need to be shared among everybody who wants to use them. So anything that is not given an advantage by a QPU, you want to still do on a CPU or GPU, okay? But you only want to send things into this box when it's actually going to get you some level of advantage. And then in here, we just have kind of graphical representations of that block diagram I had previously, right? So this the classical host, real-time host, is just kind of your standard server. This, I believe, is the 9680 6U air-cooled. So a beefier thing that can hold either 4 or 8 GPUs, a lot of compute in there. This is a picture of a pulse processor. So that's a digital analog signal conversion with timing windows. And then the QPU is not actually this device. The QPU is down here. This is a chandelier. It's a dilution refrigerator. Or it's the chandelier inside a dilution refrigerator, to be specific. And so I mentioned there's a lot of different ways to do quantum computing. One of those ways is by a device that sits at about 10 millikelvin. So that's 1/100th of 1 Kelvin. So very, very, very close to absolute zero in order to bring out the quantum effects of these systems, right? And actually enable you to do superposition and entanglement. And so this is, this kind of delicate ecosystem, but you can sort of black box this system as the quantum accelerator that you have access to from within your HPC environment. And just a quick note on the, and it looks like some of the fonts came out poorly here. I apologize for that. But just a quick note on the software environments here. There's this idea, there's got to be all kinds of fancy applications I need in order to do quantum computing. Not really true. A lot of what you're touching is going to be your standard interfaces already. So you can start in Python. Within Python, you can use a framework called Qiskit. I'll call that out specifically. It's the one I probably use the most, which is just a way. It's an open source framework hosted by IBM for writing quantum circuits in Python. And when you get down to the individual gate instruction level, you're just kind of putting them together one after another in some way that implements a quantum algorithm. But again, you're using Slurm. I said we're going back to HPC. Slurm is a standard tool used in the HPC environment. So if we are making this accessible to HPC tenants, we need to meet those tenants where they're at. We need to use the tools that they're used to using. So Slurm is one of those. So Jupyter Hub, if you're familiar with Slurm, practitioners will be well aware of. And then there's some highly specialized frameworks in here for creating quantum algorithms. But again, the goal of the industry is to bring it down and make it approachable and lower the barrier to entry. So that's what we're working on doing. And then from there, this is cloud access, not on-prem, but then from there you access the QPU either on-prem or through an API. Okay, so that's kind of the workflow I want you to have in mind as we go forwards. Next, I want to speak specifically to the intelligent quantum computing platform. So if you go back, if we real quick just stay on this slide for a second. Again, I talked about the specs of this server here, and I said it's got 6U of air-cooled, like 4 or 8 GPUs. This is chunky. This is a chunky server, right? So you say, okay, well, we're sitting right next to this HPC. Why does the host for the QPU need to be so chunky, right? And the answer is because having that framework, having that close by node and very, very low latency connection to the QPU, about as close as you can get, enables you to add value to those quantum workloads. And again, remember the principle. The principle is we want to use as much CPU and GPU compute as we can and minimize the amount of QPU we have to, because the QPU is the scarce resource. CPU and GPU we have, right? So anytime I can add value to a quantum workload using classical resources, I want to do that. And so in service of that, my team in Dell's research office have been working on and maintaining what we call the quantum intelligent orchestrator. So the quantum intelligent orchestrator up here, QIO, is essentially that. This is an application. It's an MVP, proof of concept, MVP, POC, ASAP thing that we maintain, that we work on. And the goal is to show one possible way, and there's a lot of ways to do it, but the one possible way to make use of that chunky server that sits next to the QPU. So I say, we're going to add value to your quantum workloads with this low latency GPU compute. Okay, how? Right? What are you actually doing? So that's in this box here. So hopefully y'all can read that okay. Circuit cutting and knitting, let me leave that to the side. We'll get into that in a slide upcoming, so I won't worry about that right now. Runtime prediction, this is important. So this is a custom ML model we made to estimate runtimes. That's important because again, QPU time is expensive, and so you want to have, or it's useful to have an estimate of how much QPU time a particular job is going to compute before submitting it, because the goal of quantum computing is not just to do cool quantum stuff, but it's actually to improve outcomes for people using compute. And if I can get you something 10% faster, but it costs 3 times as much, right, that's probably not helpful. So this is one of the pieces that we need to help us orchestrate. Does a particular workload get run on quantum or not, right? Resource optimization, that's part of that same equation. How do I know when to go to a quantum device? And then if I am going to a quantum device, how do I know which one, right? So down here, you might have a driver for QPU A and you might have QPU B. So these might be services from different hardware vendors. And these different vendors will have different offerings. And so one QPU might have way more qubits, but they're sparsely connected. And so what does that mean? That means I can't always entangle this qubit with this qubit or that qubit with that qubit. I might have 1,000 qubits, but they can only be entangled with the ones like very near to them on the chip, right? Whereas a QPU vendor B might have fewer qubits, but they're all entangleable with each other. You can get a super dense connection of information. And so those are different QPUs that might be good for different kinds of problems, right? This is, if you know any linear algebra theory, right? This might be useful for a sparse matrix computation. This would be useful for a dense matrix computation, right? So it's how the data relates to each other. So when you have a quantum job, it's not just a matter of do I send it to a quantum device or not, but also while we're still in this era of competing standards, it's also which quantum device would I like to use. So we have an ML model for that using some of this information, qubit availability and connectivity, things like the error rates as well. Error mitigation algorithms. So qubits are not perfect. They are noisy. We are not in a world where I can do perfect quantum computation. There is a significant error overhead. Most of the QPUs out there right now are best suited for research and experimentation. They're not kind of production grade yet. So, some of them will say, oh, we have a 99.9% fidelity on our qubits. And that's useful for some things. But if I told you that 1 out of 1,000 times you were going to do something on your laptop, it would go wrong, you might say, oh, that's kind of low, but I assure you that would get very old very quickly. But beyond that, that's a figure that applies to an entire job. So again, if you have a single quantum job that spans 10,000 instructions, that means at 10 points, statistically, at 10 points along that iteration, something will go wrong. And when you're doing something like factoring a large number, right, or you're doing a search algorithm or these other various quantum algorithms, if you have 10 errors along the way, almost surely your end result will be off, right? You can't almost factor a number. That's not helpful, right? Being off when you do that is not going to yield results. You need an exact answer. So something we're working on is saying, well, we can do, you can actually detect when there's been an error. There's a lot of different ways to do this. I won't, this is a whole scientific discipline unto itself, but suffice to say, with a significant amount of GPU compute, you can analyze the results coming out of a quantum device and help determine which runs in the quantum device were made in error to some degree. And if you throw those errors out, it will clean up the signal from the noise and it will make it more likely that you're able to infer from the quantum results what the actual solution to your original problem was. It's worth flagging here. I say multiple runs because of the error rate right now, because of the error rate and the statistical nature of qubits. Most jobs on quantum devices are done hundreds, if not thousands of times over and over again. They tend to be extremely quick, so that's not super expensive necessarily, but you do that to get different results. And then you actually, what you're looking at are not the individual zeros and ones that you measure on the qubits, because again, to go back to the server, they need to be either 1 or 0, up or down. So we convert them back to digital before they go to the server. But you don't just do that once, you do that a whole lot of times. And then you've got a lot of different bit strings. And it's that distribution of bit strings, this one's common and this one's common and this one's common and the rest are fairly rare. That's where the actual information from the quantum device is contained. So another application of GPU compute here is just looking at those distributions using an ML model. Again, a lot of this is ML powered, and using an ML model to extract what likely was the result of error and dismissing those results. Queuing optimization, I think that's rather explanatory. Optimize the queue. Explainability post-processing. This is just, again, that idea that I'm going to get out ones and zeros, but my original question was, I was doing molecular modeling and I was looking for an energy level of this compound when it's settled into its lowest energy setting. So you just gave me a bunch of zeros and ones. Okay, so I need to actually take that information and reinterpret it back in the context of the original problem that I submitted to the quantum device, and then continue on whatever pipeline I was already running. And so that's another job for this particular node. So again, all of that is happening that I described. All of that is happening in here. And everything that I just described is also happening in non-real time. So this is all pre and post processing behavior. Okay, so that's why I'm keeping it on this side, which is application time. So this is large scale application. So this is the slow behavior at this millisecond level. So milliseconds are considered slow here. Then we move into what's happening in this real time layer. So now we're talking about a lot of the communication between the control plane and the QPU, right? Or instrumentation to calibrate the device in the QPU. This is when you get into this, I guess, I forget the acronyms, microsecond latency time. And now, so again, here I said, with this error mitigation, I said, what was likely the result of error? And if I detected there was error, let's throw out that result. Now, here you actually get to do error handling. So what is error handling? The qubits only stay in superposition for a short amount of time, right? They don't want to stay both up and down, 0 and 1. That's not kind of stable for them. They eventually interact with the environment, they lose that superposition, and they collapse, right? That's the collapse of the wave function. And so they can only stay like that for a very short, microsecond amount of time, right? So if I'm going to operate with them dynamically, I need to be able to respond at that speed. So now error handling says if I can get that latency down low enough, then I can actually intercept the quantum information while it's still in superposition. And so that's what's happening here. Error handling is saying, not only can I detect error, but I can do something about it. If I detect that there's been an error, because it's kind of the equivalent of a checksum. There's like a checksum that happens at various stages along the quantum computation. And I determine that there's an error with that checksum. I can correct for it in real time while the qubits are still in superposition. Again, this is highly, highly dependent on the architecture. It's dependent on the QPU. It's very delicate. It's tough to do. It's not productized yet, but this is our path towards improving that 99.9% figure that I mentioned before. The actual physics of it are only going to improve so far. We need to be able to do things like apply redundancy to the qubits and do this real-time error correction if we want to hit a level of accuracy that's actually acceptable, where you can do a 10,000 gate long instruction and get out a meaningful result at the end.
Burns, We have a question in the Q&A.
Please,
Yeah,
please.
so it's are you considering native parallelization within the workers themselves, or is the parallelism to be handled only at the orchestration layer? If they are parallelized automatically, is that where the error handling is done?
So we're right now for the MVP, all of the parallelization is happening up here. We're not kind of parallelizing in here. At this level, when we kind of get down to the QPU drivers, we sort of expect whoever is maintaining that QPU to make available that level of advantage to us. So here we'd be sending off, by API these jobs, and what they do under the hood is kind of their business. We just get out the results from them. Um, we'll talk about quantum emulation in a little bit, but when you do quantum emulation, there's some parallelization tricks you can do. But yeah, right now it's kind of high level. Um, and again, this is not. I'll take a step back too and just say QIO is not. This is not a productization effort. This is not something that we're making out to be available. So we understand it's not totally optimized. Again, a lot of it's written in Python, but if you want a performance, you might want to rewrite and Rust or C++ or something. So proof of concept stuff here, definitely more parallelization advantage to be had. And I love that question because it's very insightful. So whoever asked that, I would encourage you, to take a course in quantum computing and see what you can do. Maybe you can improve on the state of the art. And it looks like, oh yeah, great. And if anybody else wants to just come off mute and ask questions anytime is good. Yeah. So in terms of what else we're doing here at this co-location level, calibration is extremely important. So again, we're sending pulses, radio frequency pulses down at very, very specific frequencies. So that means having the QPU tuned to a particular resonance. If you get outside of that resonance window, then the instructions are not going to take. So also understanding that back and forth of that analog signal is something that's very, very delicate, very important, and very sensitive to timing. So keeping those resonance windows right in the sweet spot as you're doing computation and between computations is something that you really truly need that timing window for, because if you can't catch it in that nanosecond time, then it's just going to get out of hand more quickly. Like if you can't respond before it's changed again, then there's no reason to calibrate it in the first place. Instrument control, again, how are we actually doing this? When we send the pulse level instructions, sometimes they just go down analog signals into the cryogenic refrigeration system and control the qubits. But for other systems, for example, neutral atom QPUs, they'll use lasers, right? So now you're not only just controlling these signals, but you've actually got real lasers, and the lasers are being split because if you have 10,000 qubits, you can't have 10,000 lasers. So you have to have a handful of lasers. The beams have to be split. There's really a lot of effort that goes on, especially in this box, that we wouldn't have time to talk about today. But again, it's very important that it happens in that nanosecond timeline, but is still wanting to be accelerated by your big chunky server with the 8 GPUs on it that's co-located with the QPU. And then this physical time layer, nanosecond, is really, you're just talking about the qubits themselves and whatever control plane you have right up there. But I mean, that's when you're really talking about entanglement, coherence time, those kinds of questions. All right, I think, oh yeah, there we go. So how do you actually bridge this gap, right? I mentioned using the GPUs on this server to do something over here, right? To do calibration and error handling. And you say, Burns, what are you talking about? This is over here in this side, and that's over here in this side. Why would you put them on different sides if it can do that? And the answer is we're leveraging something called NVQ link. So if you're an HPC nerd like me, you've probably heard of something called NVLink, which is a way of connecting two or more GPUs together so they can share memory, they can compute together, you can treat them as a single resource. NVQ link is sort of similar in the sense that you're connecting disparate resources to the same framework, and you're connecting them with as low of latency as you possibly can, so you can do that. So again, if I'm going to use the GPU to do, and I'm especially calling out these two tasks, if I'm going to use the GPU to do it, then that means I need to be in this nanosecond time realm. And so NVQ Link said, or NVIDIA said, we want our GPUs to be able to be used as the calibration engine and error correction engine for qubits. So what we need to do then is we need to get this layer, and this is the things that we're really connecting. We need to get this layer down as quick as we can, right? I need to go between the pulse processing, again, that's the digital analog signal conversion, and the beefy GPU compute as quickly as possible. So NVQ-Link framework says I will get that latency down to within 4 microseconds. And they did it as a lab experiment. And so then we at Dell said, well, we want to be able to promote, using our products as the classical control electronics for QPUs. So we needed to validate this. So that was something we did earlier this year. Is we validated the NVQ-Link framework and achieved a sub 4 microsecond connection between an FPGA and our GPUs in our box. And I say FPGA because these pulse processing units are FPGA powered. The major vendors use FPGAs to actually do the signal conversion and timing windows and that stuff. So this is specifically, the NVQ-Link framework is specifically connecting the FPGA in the control box to the GPU in the server. And if you look into it, one way they do that is that when you get a signal back into a server, right, the first thing that happens is it goes to the CPU and asks the CPU what to do, right? Because that's how computers operate. That's why C in CPU stands for central. It's the hub. But that's too slow. If I got to go to the CPU and the CPU says, no, go to the GPU, and then the GPU says, okay, here's the answer, goes back to the CPU before the CPU says, okay, FPGA, here's your answer. That's too slow. Okay, so part of what NVQ-Link does is it actually hops and it goes straight to the memory access from for the GPU. So you're doing things like remote direct memory access, RDMA, and your CPU hopping to get straight onto the memory for the GPU. Again, okay, maybe that's too many technical details, but it's a cool project. I'm really proud of it. All right, so moving forwards, again, what does this look like? Where do these different nodes sit? So now that we have the NVQ-Link framework, you can actually put this particular real-time host server in this nanosecond realm. Okay. Microsecond realm. Nanoseconds over here, so microseconds here. And you can see, yeah, RDMA over converged Ethernet is the technology being connected there. And then here to here, you can just do whatever. Here to here, you can even just, run a Cat6 cable or something. Oh, and there's our announcement. We're so proud. What is this? This is other material. Okay, so I left off one component, and that was something called circuit cutting. And I said, oh, I'll come back to that. And I didn't know if I would, but the slide's in here, so I will. Okay, so what is circuit cutting? Again, let's think back to the idea of what we're actually trying to achieve with this host server. What we're trying to do is we're trying to provide as much advantage as possible to the QPU. And so one of the main constrictions of modern day quantum compute devices is that they're just simply not big enough, right? We can get 30, 40 qubits, but 30 or 40 qubits you actually provably can't get an advantage over classical compute. You need 200 logical qubits. What a logical qubit is, I'll get into in a little bit. But suffice to say that really getting enough qubits in one place and controlling them all effectively is a huge bottleneck right now. So if I have a useful quantum circuit, it may require more qubits than I have access to attempt to execute it. So what circuit cutting is, it's a means of taking a single large quantum circuit instruction and breaking it down into smaller ones. Now, the unfortunate thing is I can't take a 50 qubit circuit and cut it into two 25 qubit circuits, except in very special cases. Generally, that's not going to be how it works. You're actually going to pay kind of this exponential toll, right? Because if you could do that effectively, there'd be no quantum advantage, right? So when you're going to have to pay an exponential toll to get that increase. So eventually, as I reduce the number of qubits, I get more and more of these split circuits. So I could get 20, 30, even 50 or 100 sub-circuits from that original quantum circuit. But again, if it lets me run my job on the quantum device I have access to, well, no matter how long it takes to run those sub-circuits, a long time is still better than impossible, right? So Circuit cutting is one way of saying if I don't have quite enough qubits on my device to run my quantum circuit, then I can cut that circuit into smaller subcircuits and run those in sequence, right, on the QPU I have access to. And then at the end of the day, I take the results and I squish them all back together and I pretend it was a result for my original circuit. Again, I have to stress that this kind of helps around the margins. It can't take you from needing 200 qubits and fitting on a 30 qubit device. It's really a handful of qubits that's going to save you. But again, if it means your problem takes a long time instead of being impossible, it can be useful for it. The other thing I'll flag here is that we've got this specific count 33, and we're putting CPU and GPU down here in the resources. And so that's because, yes, you can run quantum circuits on quantum devices. That's the point of them. But up to a certain qubit count, you can emulate them. So emulation is the process of taking a CPU or GPU resource and pretending for a minute to be a quantum device and saying, okay, you've got these qubits and you've got these instructions. What is the state of the QPU after you apply these instructions in this order? And what's really difficult about that is because, like I said, when I was talking about molecular simulation, classical resources are really bad at understanding quantum behavior, but they can on small scales. So until you get up to about 35 qubits, you can run what's called emulation of a QPU, where you actually track the entire state of the quantum system, and you apply the instructions and you understand the result. So the advantages are that it's not noisy. So again, there's only 99.9% fidelity for a lot of quantum operations. In emulation, it's 100. It's the accuracy of your computer, and if your computer is already running error correcting code, then you don't need to worry about error. So it's perfect fidelity. There's no coherence time issues because it's not actually qubits, right? You're just emulating them. You're pretending. You'll also see it's called quantum simulation, but that's wrong, and I will die on this hill. It's quantum emulation. So for the recording, I want to just anybody watching this, quantum emulation is the process of CPUs or GPUs pretending to be a QPU. Quantum simulation is the first thing with molecular compounds. So it's better if you can emulate it, then you can just have perfect fidelity, perfect qubits. Everything's good. The only killer is that you're only going up to about 35, maybe 40 if you really stretch it, qubit count, and anything larger than that you need an honest goodness QPU. But again, if you're splitting it and you do circuit cutting and you get that circuit size, the subcircuit size down within that 35 qubit range, then you can use emulation and you can run them in parallel. The gap, what turns out to be tough is the memory footprint. So it's very memory intensive to do quantum emulation, and that's what's bounding us from going any higher. So you can get access to larger memory pools, you can do larger emulation, but each additional qubit doubles it. So I think it's something like for 35. So for like 30 qubits, you need a 50 or 100 megabytes or something of memory. By the time you get to 35, you're at I might have that. I've got it later in the slide. I won't. Let me not put my words to it. But basically, once you get to like 40 qubits, you need 100 terabytes of memory. So that's why beyond that it becomes unfeasible. And then you need 200 terabytes and 400 terabytes, etc. So you don't bother with emulation past a certain scale, but it's a really useful tool for hello world quantum algorithm development, bug fixing, that kind of thing. Okay. If I end up I do want to talk about Cubo, but I don't know if I want to do that now. I guess I will do that now. This is a good chance. So this is going to be a little bit of a logical break from this point forward. So if anybody's been sitting on a question or just wants a breath, maybe now's our chance for that. Me, I want the breath. Okay, cool. So I said that there's a lot of different ways to do quantum computing, and I've been describing a lot of things about gates and quantum circuits, and that's one large pool. That's kind of the main way to do quantum computing. But there's another approach to quantum computing called quantum annealing. So quantum annealing is less deterministic. Instead of applying specific instructions to individual qubits and entanglement instructions and superposition instructions, What annealing does is it's a way of organizing your problem, your workload, into a very particular format. And it's a format that can be expressed in a physical field. So usually an EM field, right? An electromagnetic field that's contained in a physical space. And what you do is you take your qubits and you put them in that field. And since this field is representing the contours of my problem, I let the qubits sit in it. They adhere to whatever is the most natural resting place, so like the lowest energy setting for those qubits. Again, in physics, the lowest energy setting is the place the system will always settle. It's the most stable, right? So you let it sit for a while until it comes to its low temperature, which, funny enough, is where the word annealing comes from. I believe annealing was originally um, a glass blowing term, if I'm thinking of the right word. What's it, annealing? I think you can look it up. But the point is that you let the glass settle slowly over time until it hardens and takes its eventual shape. You're doing the same thing with analog quantum devices, quantum annealers. Um, and again, in order to do this, though, you need your problem to be of a very specific kind. It needs to be something called a QUBO. And a QUBO is just a shorthand for saying these are the hallmarks of a problem that actually can be encoded into that kind of landscape that you apply to the qubits. So QUBO is quadratic, unconstrained, binary optimization. And that last one's important because you're specifically talking about optimization problems. So now there are hacks and there are ways in which you can take a problem that's not really truly an optimization problem and kind of turn it into an optimization problem. Um, so like if you had, yeah, I won't go into it here because I'll go into it in a little bit. But basically, it sounds like it's extremely constraining, and it is somewhat constraining. It's certainly not universal, but it's maybe not as constraining as you might otherwise think offhand. Binary just means all of your variables must be binary. You can have integer variables, you just need to encode them into multiple binary variables. Okay, unconstrained, I'll talk about. And Q is actually quadratic, not quantum. So Q just means you're able to deal with second order terms in your optimization problem parameters. So you might have an objective function with degree 2 terms, and really the comparison we should be making is against linear solvers. So mixed integer programming models, linear programming models, those are all these linear operators that we're very, very good at because computers love thinking linearly, right? But this will allow you to go to higher order. This is QUBO. There are actually ways of doing third order, fourth order. They're called HUBO, like higher order binary optimization problems. But essentially, right now you can just think of it in this format. So suffice to say, if I'm going to summarize all that, there's a parallel way to doing quantum computing, which is more restrictive in terms of the kinds of problems. So why would we do that? If it's more restrictive, why would we do it? The reason we would use quantum annealers and force ourselves into these QUBO formats is because they typically come with higher qubit counts. So instead of 100 or 200 qubits, you might have 5,000 or 10,000 qubits. So you can all of a sudden deal with larger jobs. So currently, this will change as the hardware evolves, and this could change if you're watching this recording back in 2 years. It likely has changed, but for now, if you have a certain production grade problem that you really want to implement, and it's a large scale problem, which it usually is if you're trying to get some quantum advantage from it, you may be forced into using an annealer based on just the raw size of it. And that's where you will need to implement this kind of QUBO file format. And so this slide, I know what I've been saying hasn't really been on this slide. This slide is just kind of saying, hey, we can do something similar that we've done for the gate-based models. We can do the same thing for annealers using QUBO. It's very similar. Again, the architecture is entirely the same. It's just using this kind of plug-in based system to apply these value adds by the classical hardware. So again, the principle is exactly the same. It is to use the classical resources as much as one possibly can to provide as much value add to the quantum workflow overall. And so you do it in a slightly different way because because the file format and the architecture is different, but the principle is the same. And some of these things, runtime prediction, parallelization, like those are similar concepts as well. Okay, so I did want to specifically go into this because I like to include a particular use case we've implemented at Dell, and this was actually based on Cubo. So again, I said very specifically, if you have a production grade problem, you are probably dealing with something fairly large, right? And so if you're dealing with something large, then you may need to go this route of using an annealer. And so we looked at problems inside our organization, and we said, how can we be customer zero, which is how can we take these emerging technologies, and if we're going to advise people to adopt them, we should know what that process is like, and the best way to do that is to go through that process ourselves. So my team said, what is one of these places where I have a large problem that we can't necessarily optimize already because it's it's combinatorially difficult or it's compute intensive, right? But if we could improve on it, would have a lot of impact. We're like, there's some things if you could make them 1% better, people say, okay, I don't really care. It was already kind of good enough, right? But we went to the supply chain, and the reason is the Dell supply chain is massive, right? It spans 100 billion different countries and 37 different continents. It's crazy. It's this huge gargantuan thing. And so if you think of the Dell supply chain, right, where our parts go and ship them to and everything, you can imagine the total like transactional value of that supply chain. Now you think, okay, if I could make that 1% more efficient, you start to think about like the order of magnitude of dollars involved. That 1% is probably extremely impactful, right? Even if you only slightly improve it. So that's where we said, okay, maybe that's somewhere where we look where there's these large intractable problems with like combinatorial explosion. But where if we could improve upon it, it would really move the needle. So I spent about 6 months more or less interning with our supply chain team to understand how our system worked, to see if I could identify one of these problems in there that had the right features that I was looking for, where it would move the needle. And so I found one process we went through, which the procurement allocation optimization problem. And basically, this is a way of figuring out of our parts, and our CFGs, I think, are common functional groups. It's this like supply chain jargon. We buy from these various suppliers to various locations, subject to certain constraints. And this is something we have to run all the time because we need to know what our procurement is from our part vendors. And this is a massively complicated endeavor. So we have LTAs. These are long-term agreements. These are contractual agreements with our vendors. So, kind of important contractual agreements. Supportability by products. Day sales index. This is a backstock requirement. So I want to know if a particular site is to stop receiving new shipments for some period of time, I need to ensure that they can remain productive and producing products for some amount of time until that disruption is cleared, right? If there's a weather event or they miss a shipment or something, I don't want an entire factory to shut down because they ran out of this kind of screw, right? So keeping some level of backstock, that's another constraint in there. And then vendor TAM mix, this is just saying, that kind of on the opposite end, I want to get a mix of parts from different vendors, so that way if there's a disruption, not at the receiving end but at the distribution end, if there's a certain supplier has an issue with supply one quarter, again, we're not left totally high and dry because we got 99% of our stuff from that supplier that quarter. Okay, so this is a lot. There's a lot of constraints going on here, and it's a fairly complicated problem, which was perfect for what we were looking for. So put into kind of words like this, this is contractual agreement for purchase of various parts. This is the distribution among different vendors. These are all this completely made up numbers, obviously, but this is kind of the spirit of it. And then this is the backstock requirements. We had to fill all these constraints at the same time. And what we found, and I thought this was very funny, is that more often than not, this is not possible. This is actually an over-constrained problem. I didn't realize that. I was talking to the person in supply chain. They're like, "Oh yeah, this one didn't have a solution." I said, "What do you mean it didn't have a solution?" They're like, "Yeah, it was over-constrained." And so then what they would need to do is they would need to go in here and adjust these. So they would change it, and instead of 3 to 5 weeks, they'd adjust it maybe to 2 to 6 weeks and kind of expand that. Or maybe they said, okay, maybe if we drop this minimum from 20% to 10%, or actually, make more sense to drop this from 40 to 30 or something, right? We would just change the allocation a little bit, and then we would rerun it until we eventually got something that was useful. This is one we didn't mess with because that was a contractual agreement, so we weren't obviously going to change anything there. But what we found is that the Cubo actually slotted nicely into this kind of problem. So if you think of the letters of Cubo, right, the U stood for unconstrained. And these are constraints. You say, how do you run an unconstrained problem if you have constraints? And so the answer is in this kind of little math trick, and I've got a slide on this in a little bit, but there's a math trick whereby you take something that would be outside of the constraints and you penalize it. So you say any answer where this share got to 45% instead of 40%, make it look to the solver like that costs us $1 billion more to do that solution. And you can do that. It fits in the solver just fine because it's not a constraint. It's just a different weighting on your objective, right? Originally, our objective was to, fulfill all these constraints and then obviously spend the least amount of money doing it, subject to those constraints, right? So if you tell the solver, oh, and if you go out of this bound, it's going to cost you $1 billion, then it's not going to choose that because it's looking for kind of the cheapest option. And what's nice about this is when you ran this using a Cubo, oh, and I should say this was all kind of sensitive data. So it ran on emulation. So this was emulated. This was not run on a quantum device. This was all emulated. Emulation for Cubos, works similar to emulation for quantum circuits. You can imagine the same mental model. But so we emulated this internally. And what's nice is that if your problem is over-constrained, a Cubo-based solver, a Cubo, an emulated Cubo solver, will still produce an answer because it returns back an objective, right? And so it will be necessarily one that broke one of those constraints because it's an over-constrained problem. But what it will do is it will find the point in the solution space that kind of breaks the constraints the least, because it wants to incur as little penalty as possible because it wants to return the cheapest possible result. So the art became adding the constraints. So we said this one was inviolate, so make this one worth $100 trillion or some amount. Maybe not. I forget what numbers we use exactly, but make this one inordinately expensive to break and just never break it. And then this was the next most important. So this was worth, I don't know, $10 million, and each one of these was worth $5 million. So it's like, okay, you'd prefer to break this, but if you could just break one of these instead of breaking like 17 of these, then just break the one of these. Again, oversimplifying, but broad strokes, that's kind of how it worked. So there was no QPU in the loop. This was still all on classical gear, but the point is we're using this quantum. It's called quantum-inspired algorithms, quantum-inspired optimization to change how we do some of our problem solving. And what it allowed us to do is it allowed us to reduce our developer time that was spent rerunning and rerunning and rerunning and rerunning and rerunning the problem over and over again. Quickly, I'll just touch on the second use case. We had such a great success, we did one more, and this was a very similar problem, but instead of purchasing from vendors, this was kind of the analog problem where we were rebalancing inventory across different locales. So if I have plenty of backstock over here, not enough over there, I want to ship from there to here, but also that shipment might be really expensive, so it might actually be better to get it from here. And if they're both really far away and expensive, but there's a vendor up the road, maybe it's cheaper for me to just buy new after all, and then just trash some of this backstock. Again, some of these really complicated constraints, I won't put them all here, but the idea was another one of these large scale problems that was difficult to solve, but could provide real value if it was done slightly more effectively. All right, so that's use cases. The rest of these slides talk about the intersection of AI with quantum. This is a hot topic that comes up a lot, as you can probably imagine. So again, a good break if anybody's got questions. If not, I'm just going to get some water and we'll move into kind of the last third of this. Okay, cool. So AI and quantum are an interesting pair of technologies, and they have really two intersections because they're both technologies that are meant to help enable certain things, right? Accelerate things. Like technology should make your life easier, make you be able to do things you couldn't otherwise do. And so that means two technologies can intersect in two ways, right? One is I can use quantum computing to improve results in artificial intelligence, and the other is I can use artificial intelligence to improve results in quantum computing. And those two intersections look very, very different in practice. So I've got separate sections here. We'll kind of take them one at a time here, and we'll start with the ways in which quantum computing.
Hey, Burns, your mic is not working. Hey, Burns. Hey, Burns, I think you just unmuted yourself.
Yeah,
Thank you, Lori.
I'll ping him internally and tell him.
Thank you.
Sure.
All right, how far back did you lose me?
There you go.
Yeah. All right. Where was I? Okay. So variational quantum algorithms. I said some really amazing stuff on here. Actually, my first few sentences are spectacular. So if you miss those, I feel really bad. No. Variational quantum algorithms. The point here is that I mentioned on the architecture slide that the goal is to keep your classical compute and your quantum compute kind of as closely tied together as you can. And that's primarily because you can do really cool stuff like we spoke about that adds value to your quantum workloads with your CPU GPU compute. But another reason to keep those low latency connections alive is that there's actually dedicated quantum algorithms that are using both resources in tandem. So a variational quantum algorithm will actually go from QPU to either CPU or GPU back and forth iteratively. And the reason these are really, really important, especially right now, is that I mentioned quantum superposition decoheres, right? And you lose that extra advantage. And so one way of mitigating that downside is by doing short bursts of computation rather than long monolithic blocks of quantum algorithms. So what a VQA will do is it says, let's design something where I do a short burst of quantum behavior. I feed the results back to a controller in the classical plane, which updates or iterates something based on that quantum run, and then provides a new updated quantum job to the QPU to then run. So this is quantum machine learning works this way. So machine learning is based, I don't know the background of this particular audience, so I don't know if I can use dedicated ML terms, but a lot of ML is based around something called gradient descent, whereas I'm looking for a global minimum over a large energy landscape over a lot of variables, right? And I want to find the lowest energy point in this large energy landscape. And to do that, I just find which way is downhill and I go that way. I take a few steps, and I find the new way which is downhill and I go that way over and over and over and over again, right? And this is actually one way you can use quantum devices in the AI workloads is you can use QPUs to do that finding, that navigation each time you take a step, right? And then you update the direction, you do a new quantum computation, you move in the energy landscape, and you kind of go around in that circle. Right now, again, I want to caution there's not an actual quantum advantage to doing that with a QPU right now, but these are just some of the architectures of these algorithms where you have some important quantum information wrapped up in a quantum circuit. You do a classical computation based on the result of that provides a set of parameters theta. Those theta will actually form a new quantum circuit to be run by the QPU, and you keep refining and iterating on that quantum circuit to get to some specified place. So with that being said, then you don't necessarily need to keep it in that topology, right? This is saying we're going back and forth between QPU and CPU, but there's no reason you have to go back and forth exactly between those two devices. So the broader picture is the idea that you have many different resources, right? Even within the server world, you have CPU, GPU, DPUs, FPGAs, NPUs, neural processing units. You have all these different compute resources. And right now, one of the big challenges for developers and compute stakeholders is to find efficient ways to use those different resources, know when to go to a DPU, when to go to an NPU, when to use my FPG, et cetera, right? Same thing is true when you include quantum accelerators into the mix. I might have a really densely connected trapped ion device, or I might have a really large qubit count superconducting device, or I might have a really long coherence time neutral atom device, right? All of these different quantum processing units that have their own strengths and weaknesses. And so again, we're not necessarily going back and forth between CPU and QPU, but we might be going along this workflow where every step of the way after I do something, it's updated and I say, where do I go next? Based on what just happened, what resource makes the most sense to access? And again, you can imagine a really heavily heterogeneous compute, say data center, which has multiple different QPUs on site, and then the servers are equipped with different processors. You can imagine a sort of playground where, as a developer, as an engineer, you get to design these workflows that have access to all of these different devices. And where you go next is just dependent purely on what's going to make the most sense, what's going to provide the most advantage. So again, that's sort of the idea, the way we're looking at incorporating new quantum devices into ML and AI workspaces, essentially by saying that AI is just an extremely compute hungry industry. Both training and inferencing consumes a lot of compute. QPU provides compute. It's kind of that simple. It's not, but we like to pretend that it's that simple. But providing more options will always be better. Having additional options to tailor to different workflows is going to just mean that we can do more in the future. All right. So quickly, we'll do the other side of this, leveraging AI for quantum. So again, we talked about what quantum could potentially do for AI going forwards. Now we'll talk a little bit more about what AI can do for quantum. And before I even go into these slide decks, because this gets a little bit dense, but high level view, AI is, especially generative AI, is very good at, I think, empowering people to learn more and to do more. So we have coding assistants that can help people that are more novice coders get to a working MVP, say, more quickly, right? Again, how do you harden and productize? Like that's another story. But at least that working prototype stage can be greatly accelerated with AI tools. Same thing is true here. We don't naturally think in quantum workflows. I've been doing this for 5 years. Even I don't think naturally in quantum. It's a very kind of mind-bending place to live. But AI tools are a sounding board for me. Every day I'm talking to Claude or I'm talking to ChatGPT about how to think about this particular kind of entanglement, how to think about this particular phase symmetry in this quantum environment. And I find it's just a lot faster. It's all information you can get elsewhere, but it's just going to help condense it. You can interact with documents, you can query textbooks, you can say, how do I think about this? So at the very, very base level, AI is going to be a great accelerant to quantum algorithm and quantum hardware development just by helping empowering the people working in that field achieve what they're going to achieve faster, understand better, understand deeper, and also communicate it more deeply, right? When I was talking to the supply chain team after the project, I handed off the tool. I said, hey, we made this as our MVP. Here it is. If you find it helpful, please use it. Don't feel obligated to. But by the end of it, they were left, with this quantum emulation tool for solving their problem, and I think that will happen more and more as these workflows become more common. And I think again, it goes back to that idea of lowering the barrier to entry, helping people who are not necessarily trained in quantum algorithms or ways to use quantum devices, helping them get up to speed more quickly is just going to provide more advantage, in the long run. So more specifically, what parts of the workflow can AI help with? Well, again, this goes back to the orchestration engine that we talked about a number of sections ago, and it's each of those steps along the way. So transpilation is the stage of going from quantum algorithm on paper to quantum algorithm in practice. So on paper, I have all of the quantum instructions I would like. I can do anything, right? Any quantum gate that I can imagine, I can write down on a piece of paper. Nothing's stopping me. But the actual QPUs only implement some set of instructions. They will only do certain things. Now, anything I can think of, I will be able to do on a gated quantum device, not in a annealer, but on a gated quantum device, I can do. But to get there, I might have to go a different way. So here you see that this Hadamard gate, right? Well, I might be trying to apply the Hadamard gate in a QPU that doesn't have that available. So if I do this rotation, I think that's what is that, a Z in there? If I do this Z rotation by pi over 2, I do the square root of the X gate, and then I do another Z rotation, that's the equivalent to doing a Hadamard gate. And maybe these are native gates to the QPU that I'm using. Again, because when I wrote this, I didn't necessarily, I might have, but I didn't necessarily have a target QPU backend in mind when I wrote it. I might want to be able to change backends, go from this one to that one, etc. So I have the idealized abstract circuit, but then if this only has a certain set of gates that it's able to implement, then I have to actually transpile it and write it down in those terms. But again, there's going to be a lot of different ways to do that. We might have transpilation that has to make arbitrary choices at some places, or the transpiling engine might have knowledge of the gate errors, right? If these are logical qubits, they exist on paper, but these are actual real physical qubits in the system. So if my circuit needs 30 qubits and the system has 40 qubits, I might even be able to choose which physical qubits I use to represent my algorithmic qubits, and I might try to choose those with the lowest local error rate, as an example. So again, a lot of choices that happen here, and those choices will absolutely affect the quality of the output. So it's a prime place for an ML model to come in and say, hey, I can be trained with reinforcement learning here because I know what a good result looks like. If I'm trained on small instances and I know the results that this quantum circuit is supposed to return, because maybe it's a circuit that's small enough that you can run it on emulation, and emulation gives you perfect information, then I can use that as a benchmark, as a target to get to. And I can say, among these different ways of transpiling the circuit into pulse level instructions, I can exactly measure how far off the ideal mark I am by using that idealized state vector out of the emulation as my target. And running through that over and over again gives you a way of doing exactly this, of saying that certain kinds of pulse instructions that are generated from my algorithmic circuit are going to be better than others. So that's one place in which we're seeing an uptick of using kind of that GPU resource on the way from end user down to QPU resource. I talked about QUBOs already, so I won't go through this, but I will say QUBOs are a little obnoxious. So again, like I said, I spent a long time with the supply chain team understanding the problem, but I also spent a long time turning the problem into a QUBO. It is extremely cumbersome. So again, my background is I have a PhD in math, and I found making this really obnoxious. So again, I won't wish this on anybody to have to go through and manually make a QUBO by hand for a particular problem. I was lucky enough that this happens to be my day job and something I really like doing, so I did. But if you are talking to somebody who is responsible for producing results in a particular industry, they probably often will not have the luxury of spending a long time and a long effort of trying to use a new method of solving a problem. They are going to need something that fits into their existing workflow. So with that understanding, what we did was we said, how can we use AI to make this process easier? So what we recognized is that I can't let this play when I'm presenting this way, can I? Can I? I can. I won't play this whole thing. I'll just kind of let it go while I speak. But basically, what we did was we said there are some common ways, like I mentioned, taking a constraint and turning it into a penalty on the objective function. That's a fairly well understood mathematical operation, right? And going from your original objective function and then encoding that into the QUBO format, or going from your integer parameters and going to binary parameters from there, that's a fairly well understood process as well. It's not conceptually difficult. It is truly just cumbersome. So what we did in this project, as an example, is we just we wrote an application that would take your set of parameters. So these are all integer parameters here, and it would take those parameters and it would encode these parameters into binary variables. So we could put it into a QUBO format, and then we took our constraints. Here's the constraints. I think the idea here is that this was a birthday party was the example. And I said, okay, I want to spend up to, I think I said up to $50 on the gift. So 0 less than gift less than 50. And I want to spend no more than $300 on the decorations and the refreshments put together. Obviously, this is kind of a ham-fisted example, but and I wanted to spend between everything combined, including the gift, I wanted to spend all $300 available. And I had an objective, and I said, how happy is this going to make my daughter? I have 2 daughters, right? So I had them in mind when I was coding this. And I said, okay, she's going to enjoy the refreshments and she's going to enjoy the decorations, but she's really going to care about the gift. So in terms of how much she enjoys the birthday party, the gift is twice as important to her as the decorations or the refreshments are. Okay, just, yeah, again, a cute example, right? And then from here, the application will go and will turn this into a Cubo that can then be sent either to a quantum annealer, or in this case, an emulation engine on the server. Interesting little note here. You'll see the minus signs because again, what this is going to do, like any physical system, it's going to minimize energy, right? The ball is going to roll to the bottom of the hill where it's expended all of its potential energy. It's not going to spontaneously go from the valley up the hill, right? So when you're writing these objective functions, they all need to be minimization. So you can take a maximization like we did here. This would be, I want to maximize her happiness, not minimize it, hopefully, if I'm a good dad. So we take that expression, and then you just take what you're trying to maximize, and you just slap a negative sign in front of it. Okay, so it just reverses all the signs. So any maximization problem is trivially made into a minimization problem. And so this goes in, and we take those 2 files, we upload them here, and it produces a Cubo. So it spits out this Cubo problem, and it does all of that cumbersome work that one would otherwise have to do by hand. And then again from here, we did simulated, rather emulated annealing, and we say simulate here, but that's wrong. It should say emulate. Scrap that. But again, and these are some hyperparameters that go with annealing, so you don't need to worry too much about what they are. They've got some default values in there. So here we'll actually go through, and it should, I don't know if we included it in here. Yeah, and it should come up with the result, right? So by the end, it actually gives you an answer to your original problem. And so unsurprisingly, it says spend the maximum amount of money on the gift because that's going to make her twice as happy as everything else. But notice that it didn't violate the constraints, is really the important point here. And it will even check that, check that it met this inequality, because there's no guarantee, right? It could go outside the constraints if the penalty for going outside the constraint was low enough that it made more sense to do that rather than to choose something within the constraints that didn't do as good a job optimizing the objective function. Okay, so I'm supposed to be talking about AI, right? This is deterministic. This is not AI. So what's the next step, right? The whole goal of this endeavor is to reduce the barrier to entry, to make it so that you don't need a math PhD to write Cubos for a quantum annealer, right? Because if you have to do that to use a quantum annealer, nobody's going to use it. So this goes from these files, these CSV files, to a Cubo. So you say, okay, well then what's next? What's next is you go from a natural language description and then use an LLM to go to those files. So you go natural language description of the problem. Hey, I'm having a birthday party. My daughter is turning 7. She loves unicorns. I have this much money to spend on it. And then it will go through and it will first generate, it'll go through and it'll generate those CSV files. It'll generate those CSV files, and then it will go through and it will emulate. And so now all of a sudden you have this pipeline that goes from natural language description of the problem to, hey, here's the answer to your problem, right? You can even use an LLM on the back end to take the Cubo output. Actually, you need to go from the Cubo deterministically back to your integer parameters, but then the integer parameters, you can go LLM back to a natural language description of the answer. So you can go natural language input, natural language output. Hey, what should I do about this? Well, what you should do is you should spend $75 on the gift, maybe unicorns because she likes those, blah, 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 blah. And you've actually, at that point, achieved some quantum advantage in the middle there, completely blind to the user. Again, this is all prototype MVP. This is not part of like a product roadmap or anything like that. But the goal is to show that it's possible. You can build these tools. You can build various AI assisted applications that will eventually have the outcome of making it more accessible to use quantum acceleration from these new devices, and not require these hyper specialized math formulations and specific arcane ways of interacting with quantum devices. I know there's kind of 10 minutes left here. There's not a whole lot here left in the deck, so I was really hoping if there were questions at this point we could chat about those. I mean, I can go. I'll talk about quantum for 17 more hours. That's not a problem. But I do want to give a chance for anybody to jump in. Not 18 hours, though. That would be too much. Just 17. Did it stop sharing? I lost it on my screen. Oh, no, there we go. I don't know why that happened. Yeah, I mean, if not, maybe I'll just kind of end on this one slide where we talk about. I've got these talking points we use when we have these engagements, with customers or with partners, where we talk about this process of adoption of quantum devices, and we kind of break it down into these 3 high-level buckets where we say discover, identify, deploy. That'll come up in a second as soon as I'm all the way back through this slide deck. Where'd it go? There we go. And essentially, at some point, quantum computing will touch your lives. I can guarantee you that. And the idea is, if you're somebody who is in a field where you have the potential to be disrupted or to really gain an advantage with quantum computing, again, I'm thinking financial, like banking and hedge funds are definitely very interested in this technology. Again, for that same heuristic, if you're talking about $10 billion of assets under management for a hedge fund, right, and you make a 1% improvement or even a 0.1% improvement, right, that's a lot of money. So that's one place we're seeing these things get a lot of interest. But healthcare, we're seeing a lot of movement. Material science research and pharmaceuticals, again, for that same reason we discussed earlier. There's cryptographic implications that I won't go into right now, but I'm certain have heard that at some point. But the point is that it all stems from the same place, which is kind of understanding that quantum devices are good for certain things, but not useful for other things. And understanding that distinction first is the beginning to knowing how to use them. So knowing that they will be useful in some places, and in other places you're better off sticking with CPU and GPU. So just understanding that fact, and then what those places vaguely, what kind of questions those vaguely are, is kind of the first step to using the technology fruitfully. And then the second is taking that understanding and bringing it back to your domain, right? Whether it's healthcare, finance, whatever it is, and say, okay, I know that it's good at things like the traveling salesman problem or molecular simulation. What do I have internally that looks kind of like that? And it doesn't need to be the exact problem. Part of the skill set will also be tailoring the existing quantum algorithms to your particular use case. And then deploying, saying, okay, what are the quantum accelerators that are out there? Does it make sense for my organization to purchase one, or should we be using it on the cloud, or should I be sending my jobs to a quantum-enabled data center, et cetera? Right, all these questions, and then writing the algorithms, putting them in pipelines, understanding things around data sovereignty, right? There's all these practical on-the-ground considerations that come with deploying quantum algorithms. So, I think there's a lot of exciting times ahead for the industry. We're moving very quickly. These timelines, these roadmaps for things like quantum advantage and breaking, cryptography, certain cryptographic approaches, not breaking cryptography writ broadly. Those are getting accelerated. So it really is kind of the time to be thinking about these questions, I think. And I advise anybody, again, here or listening in the future, that beginning to think about what it means to you for your use cases for your organization or for your interests. Begin thinking about that sooner than later, because it is a heck of a learning curve. So the sooner the better, we say. All right, with that, I really will kind of stop talking here, and I'll wait in 5 minutes of silence if that's what it takes to get questions. You think I'm joking? I'm not. Or maybe I'll toss it back to Rachel, and I'm just remembering she asked me to do that.
That's okay. I'll probably take 2 minutes only. So yeah. Well, thank you, Burns, for a great session. Before we wrap up, I want to highlight a few upcoming ARC Summer School sessions. We have 2 more sessions with Dell tomorrow. The topics are fine-tuning embedded models for improved search and physical AI. We'll be closing out summer school on Friday with talks from 2 UBC researchers on their AI-related work. You can learn more or registering using the link or the QR code on the screen. Finally, we really appreciate your feedback. It really helps us to improve our future sessions. We love to learn what kind of topics you like to learn from us. The survey takes less than 3 minutes to complete, and you'll be entered into a draw for a $20 Amazon gift card. You can click on the link or use the QR code on the screen. Thank you again for joining us today. I'll pass it back to Burns to see for him to take any questions that you may have. Thank you.
Thanks, Rachel. Oh, there's a Q&A here. I forgot. I was looking at the chat, but then I forgot there's a separate tab also for Q&A. That was the
This
question
one
we
we
got
just,
earlier.
yeah, that's right.
Yeah, great. I'll also encourage, I'm accessible on LinkedIn or other places. So if anybody would like to reach out and ask questions independently by email, whatever, please feel free to do that. I'm around.
Cameron had a comment, is there's no questions, it's just a lot to take in.
Yeah, I get that a lot, actually. Yeah. Cool.
Well, if there's no other questions, I guess we could end the session here and give everybody 3 minutes back in your time. Thank you so much. Thank you, Burns. Thank you, Lori. And thank you, everybody. See ya.
Thank
Thanks
you.
all.
Bye.
Bye.